A two-dimensional truss structure is an assembly of nodes and bars, designed so that loads are only applied at the junction points. To understand how the physics of the entire system are calculated, we must first isolate a single bar from the framework. Physically, an individual bar only possesses stiffness along its own longitudinal axis. It cannot resist lateral or vertical forces on its own. When we place this bar into a global environment, we map it against a fixed x and y coordinate grid. However, the bar's internal physics operate on a local coordinate system, one that is rotated to align with the bar's specific angle, theta. Under load, the nodes of this bar move diagonally across the global grid. This means every local displacement actually involves simultaneous movement in both the global x and y directions. This creates a kinematic disconnect. We must determine two-dimensional global motion for an element that only provides one-dimensional stiffness. Finite element analysis software cannot interpret geometry visually. It requires these physical relationships to be organized into matrix algebra. For a solver to process the structure, the behavior of every individual element must be formatted into a standardized equation. Currently, our one-dimensional equation for the bar does not match the two-dimensional architecture of the global system. We need to find a mathematical bridge that translates local forces and displacements into their global counterparts. This mathematical derivation provides the essential logical framework required to integrate all individual bars into a fully automated system-wide solver. We begin with the fundamental equilibrium equation for a local element. Local forces equal local stiffness multiplied by local displacement. In its simplest form, a bar uses a 2x2 stiffness matrix acting on a 2x1 displacement vector. The variables u1 and u2 represent the longitudinal displacements at each node, but this vector is missing the lateral displacements, v1 and v2, which correspond to the local y-axis. Because the bar provides no lateral resistance, these values are 0 and are traditionally left out of the equation. As long as the matrix remains 2x2, it is computationally restricted to a one-dimensional line, unable to interact with the broader global grid. To bridge this gap, we first expand the architecture of the equation so that it recognizes two-dimensional space. We introduce redundant degrees of freedom, sliding the existing rows and columns apart to create a 4x4 matrix. We fill the new slots in the stiffness matrix with zeros and add the lateral displacements, v1 and v2, to the displacement factor. These additions function as zero-energy equations. This change in formatting does not alter the physical behavior of the bar. While the physics remain one-dimensional, the matrix is now wide enough to accept two-dimensional data. Now we incorporate the bar's angle, theta, which defines the relationship between the local and global coordinates. We use a transformation matrix, T, which contains the trigonometric functions needed to project a vector across that specific angle. Using a substitution, we replace the local displacement vector with the transformation matrix multiplied by the global displacement. We apply the same logic to the force vector. Local forces are now expressed as T multiplied by the global forces. This leaves the global force vector trapped behind the T matrix on the left side of our equation. To isolate the global force, we must move that transformation matrix to the other side of the equal sign. Algebraically, this requires multiplying both sides by the inverse of T. However, calculating a matrix inverse is a heavy task for a computer, especially when repeated thousands of times in a simulation. This step is simplified because the transformation matrix is orthogonal. For an orthogonal matrix, the inverse is simply the transpose, swapping rows for columns. Multiplying the left side by T transpose cancels the matrices, isolating the global force vector. On the right, T transpose is added to the chain. The equation is now fully resolved in terms of global variables. By utilizing the property of orthogonality, we have removed a significant computational hurdle, resulting in a clean global force equation. In our final equation, look at this specific group of matrices on the right side. It consists of the transpose of T, the local stiffness matrix, and the original transformation matrix. This cluster is the global stiffness matrix. We have successfully translated a one-dimensional physical property into a two-dimensional spatial coordinate. This formula serves as the fundamental instruction inside every commercial finite element solver. The dimensional gap between local stiffness and global geometry is bridged by this matrix product. When we move from an isolated bar to a complete structure, the computer simply repeats this process. The solver takes the local stiffness and the geometric angle of every bar and calculates the corresponding global matrix. Because the calculation relies on a transpose rather than an inverse, the computer can assemble tens of thousands of elements in a fraction of a second. This efficiency is the result of the zero-padded architecture and the specific geometric properties of the rotation matrix. Complex structural simulations are not built on magic, but on the precise application of matrix manipulation at scale.